Good day, grade 12 students. Welcome to your school on the air in physical science. I'm happy to be with you today in this journey as you will discover a new lesson via radio and television. I am Kristen Tiraniesas from SDO Kawayan City. Before we start, make sure to grab your module for this lesson. Please stay tuned to DWNDFM and CMD Cable Channel 11. This video is also streamed live at SDO Kawayan City Facebook page. Now, I want you to watch attentively, listen and learn carefully to discover new things while staying home comfortably, and make sure that you're safe and at ease while studying our lesson for today. Our topic for today is all about the formation of heavier elements during star formation and evolution. Second, the atomic number and the synthesis of new elements in the laboratory. At the end of the lesson, you should be able to give evidence for and describe the formation of heavier elements during star formation and evolution. Explain how the concept of atomic number led to the synthesis of new elements in the laboratory. In the previous lesson, you have learned how the light elements such as hydrogen, helium, lithium, and beryllium were formed during the Big Bang nucleosynthesis. Nucleosynthesis, the beginning of elements. This process tells us how elements were created. We have three types of nucleosynthesis: the Big Bang nucleosynthesis, the stellar nucleosynthesis, the supernova nucleosynthesis. It explains the continuous expansion of the universe. A few seconds, 10 to 15 after the Big Bang, quarks combined and the first nuclei were formed through nuclear reactions in a process called Big Bang nucleosynthesis. This nuclei includes protons and neutrons. Then the rise of the star began. If light elements were formed during the Big Bang nucleosynthesis, heavier elements are formed through stellar nucleosynthesis. The stellar evolution deals with the various events of the star's life, from the dense molecular cloud time, when the star becomes exhausted all its nuclear fuel. The stellar nucleosynthesis. The word stellar means star. The stellar nucleosynthesis is a chemical process of forming heavy elements within the stars. This process requires high temperature, pressure, and energy so that fusion will take place to create heavy elements. These heavy elements are very essential in our environment. Some in our bodies were produced through stellar nucleosynthesis. There are different processes involved in creating heavy elements through stellar nucleosynthesis. Let us watch this video about the evolution of a star to better understand our lesson.
Like fireflies on a still summer night, they gently dot and illuminate the infinite velveteen sky. Stars, be they millions or billions of years old, are all born in nebulae, clouds of dust and mostly hydrogen gas. Within these stellar nurseries, stars begin life as protostars, or hot cores formed by the collection and collapse of dust and gas. As the protostars become hotter, hydrogen nuclei inside of the cores begin to fuse and create helium. It is this chemical reaction, thermonuclear fusion, that generates a star's heat and energy and causes it to shine. Stars are categorized by a number of characteristics. One of these classifications is by surface temperature. Called spectral classes, these 7 major groups range from the coolest stars, which are designated as M, and up to the hottest stars, which are designated as O. Stars are also classified by the amount of light they emit, or luminosity. Called luminosity classes, these 9 major groups range from the small, less bright white dwarfs to the large and extremely bright hypergiants. But no matter their luminosity or surface temperature, all stars eventually burn through their hydrogen fuel and die out. Less massive stars, such as our Sun, release their stellar material into space, leaving behind a white dwarf surrounded by a planetary nebula. More massive stars instead blast matter into space in a bright supernova, leaving behind an extremely dense body called a neutron star. But the most massive stars, stars that are at least 3 times our Sun's mass, collapse into themselves and create a bottomless well of gravity, a black hole. But from the remnants of stars, heavier elements are cast into the universe, and it is this stardust that formed the seedlings of life itself.
The stellar evolution is an event of changes of a star during its lifetime from evolutionary phase of protostar until its stellar death supernova. Supernova. It is the violent explosion of a star which creates heavier elements. Synthetic pathways or nuclear fusion to produce heavy elements. We have carbon-nitrogen-oxygen cycle or the CNO cycle, proton-proton fusion, and triple alpha process. The carbon-nitrogen-oxygen cycle or the CNO cycle is a process of stellar nucleosynthesis in which stars on the main sequence fuse hydrogen into helium via a 6-stage sequence of reactions. A carbon-12 nucleus captures a proton and emits a gamma ray producing nitrogen-13. The nitrogen-13 is unstable and emits a beta particle decaying to carbon-13. Carbon-13 captures a proton and becomes nitrogen-14 via emission of a gamma ray. Nitrogen-14 captures another proton and becomes oxygen-15 by emitting a gamma ray. Oxygen-15 becomes nitrogen-15 via beta decay. Nitrogen-15 captures a proton and produces a helium nucleus or alpha particle, and carbon-12, which is where the cycle started. Let's move to the proton-proton chain reaction in main sequence star. This is the process by which average star gets their energy and convert hydrogen into helium. It starts with proton and neutron fuse together to form deuterium. When one proton collides with deuterium, helium-3 is formed. 2 helium collided will form helium-4. Okay, let's move to the triple alpha process. The triple alpha process happens in red giant star once they leave the stage of main sequence star. This is how the 3 helium-4 are converted into carbon. The triple alpha process begins when 2 helium-4 nuclei fuse to form an unstable beryllium-4 nucleus. If this nucleus collides with another 4 helium nucleus before it breaks apart, the 2 will fuse to form a nucleus of carbon-12. A star accumulates more mass and continues to grow into red supergiant. Alpha particle fusion. This happens at its core and creates more heavy elements until iron. This is known as the alpha ladder process. Now, how do elements heavier than iron form? Elements higher than iron requires a tremendous amount of energy to be formed. Thus, they were produced from a neutron capture reaction in a supernova. Our process or rapid neutron capture process involves rapid capture of neutrons by the atoms. It is responsible for the creation of approximately half the atomic nuclei heavier than iron. The S process or slow neutron capture process involves slow neutron capture in red giants. Alright, we have the key points to remember. The formation of heavy elements from carbon up to iron is known as stellar nucleosynthesis. This involves triple alpha process, CNO cycle, proton-proton chain reaction, and triple alpha and alpha ladder. For elements heavier than iron, like uranium or gold, they are produced in supernova. It involves the R process and the S process. During the explosion, these heavy elements are dispersed into the space, aside from gases hydrogen and helium in space. Other evidence of star formation is the energy emitted during nuclear reaction. It is also the energy emitted by different forms of radiation, such as UV, infrared, X-ray, radio wave, and microwave. Let's move to our next lesson, which is all about the concept of atomic number led to the synthesis of new elements in the laboratory. The atomic number is the number of protons or the positively charged particles in an atom. Henry Gwen Jeffrey Moseley was an English physicist who demonstrated that the atomic number, the number of protons in an atom, determines most of the properties of an element. He began his study of radioactivity in Ernest Rutherford's laboratory, but later decided to explore more on X-rays. In 1913, Moseley published a paper on the arrangement of the elements in the periodic table based on their atomic numbers. He used X-ray spectroscopy to determine the atomic number of an element. He bombarded a beam of electrons to different elements and measured their X-ray spectral lines. The atomic number indicates the number of protons found in the nucleus of each element. It also serves as the identity of an atom. In neutral atom, the number of protons is equal to the number of electrons. Thus, atomic number is equal to the number of electrons in a neutral atom. For instance, aluminum has an atomic number of 13, meaning each neutral atom of aluminum has 13 protons and 13 electrons. In general, the acceptable representation of atomic number is this symbol, capital Z. The total number of neutrons and protons in the nucleus of an atom is the mass number. The mass number represents by this symbol, capital A. The X represents the element, A represents the number of mass, and Z the atomic number. Remember, protons are positive charge, electrons are negative charge, and neutrons are neutral or no charge. Okay class, try this. Fill in what is missing. These are the solutions. His results clearly showed that frequency of the X-rays given off by an element was mathematically related to the position of that element in the periodic table. The frequency is proportional to the charge of the nucleus or the atomic number. In 1919, Ernest Rutherford successfully carried out a nuclear transmutation reaction, a process of transforming an element or isotope into another element. The reaction is written as neutron atom plus helium atom to oxygen atom plus hydrogen atom. However, both alpha particles and atomic nuclei are positively charged, so they tend to repel each other. Therefore, instead of using fast-moving alpha particles in synthesizing new elements, atomic nuclei are often bombarded with neutrons or neutral particles in particle accelerators. In 1925, there were 4 vacancies in the periodic table corresponding to the atomic numbers 43, 61, 85, and 87. Elements with atomic numbers 43 and 85 were synthesized using particle accelerators. Particle accelerator is a device that is used to speed up the protons to overcome by using magnetic and electrical fields. It is used to synthesize new elements. In 1937, American physicist Ernest Lawrence synthesized element with atomic number 43 using a linear particle accelerator. He bombarded molybdenum, or Z is equal to 42, with fast-moving neutrons. The newly synthesized element was named technetium, or Tc, after the Greek word teknetos, meaning artificial. Technetium was the first man-made element. In 1940, Dale Corson, K. Mackenzie, and Emilio Segre discovered element with atomic number 85. They bombarded atoms of bismuth, or Z is equal to 83, with fast-moving alpha particles in a cyclotron. A cyclotron is a particle accelerator that uses alternating electric field to accelerate particles that move in a spiral path in the presence of a magnetic field. Elements 85 was named astatine from the Greek word astatos, meaning unstable. 2 other elements with atomic numbers 61 and 87 were discovered through studies in radioactivity. Element 61, or promethium, was discovered as a decay product of the fission of uranium, while element negative 87, or francium, was discovered as a breakdown product of uranium. In the 1930s, the heaviest element known was uranium, with neutrons, and created an element with an atomic number 92. Early in 1940, Edwin Macmillan proved that an element having an atomic number 93 could be created. He used a particle accelerator to bombard uranium with neutrons and created an element with an atomic number 93, which he named neptunium. At the end of 1940, element 94 was synthesized by Seaborg, Macmillan, Kennedy, and Wahi. They bombarded uranium with deuterons, or particles composed of a proton and a neutron, in a cyclotron. Element 94 was named plutonium. Elements with atomic numbers greater than 92 atomic number of uranium are called transuranium elements. Neptunium and plutonium are both transuranium elements. They are unstable and decay radioactivity into other elements. All of these elements were discovered in the laboratory as artificially generated synthetic elements. They are prepared using accelerators. Imagine you're holding 2 magnets with the same magnetic poles. north to north poles or south to south poles. When you try to put the magnets together, there is a force acting upon them which makes it difficult to do so. The repulsion between the magnets represents forces between the alpha particles and the positively charged material in the atom of the gold foil, as presented in the Geiger-Marsden experiment of Rutherford and his colleagues.
Our friendly bar magnet, Barry, has two poles. He has a north pole and a south pole. He knows he can attract objects made of iron. But now he wonders if he can attract his fellow magnets. Why don't we join him as he seeks answers to his question? While Barry was walking, he saw another bar magnet on the way. He was excited to see if the bar magnet was attracted to him. As he got nearer and nearer, the bar magnet slowly got nearer to him as well, until the bar magnet's south pole was attracted to Barry's north pole. Barry was happy. Not only are magnetic objects attracted to him, his fellow magnets are too. He kept walking. He saw a cylindrical magnet. But this time, as Barry got nearer, the cylindrical magnet moved away from him. He kept getting nearer, and the magnet moved away. Why is the bar magnet attracted to Barry? Why isn't the cylindrical magnet attracted to him? When Barry's north pole came near the bar magnet's south pole, the magnets were attracted to each other. But when Barry's north pole got close to the north pole of the cylindrical magnet, they repelled each other. For magnets, when two unlike poles, the North Pole and the South, come together, they attract. On the other hand, when two like poles, the North Pole and the North Pole, or the South Pole and the South Pole come together, they repel. So what should Barry do to attract the cylindrical magnet? He should move to the other end of the cylindrical magnet. Gotcha! Now Barry knows how to attract other magnets.
So these are your assignments. Why do scientists study and synthesize new transuranium elements in the laboratory? What are the uses of these elements? Next, fill in what is missing in the ZA-PEN table. That ends our lesson. I hope you have learned a lot and gained new knowledge in this episode. For more inquiries and clarifications, you may call or text your respective teacher in this subject to assist you. Ask the help of your parents or siblings if needed. It's been a great pleasure being with all of you today. Thank you for taking the time to patiently listen to what I have to say during our lecture. Always follow health protocols and guidelines amidst COVID-19 pandemic. Remember, the more you learn, the more you earn knowledge. And knowledge is power. Again, I'm Kristen Tiraniesas, your teacher on the air. Only here at DWND-FM and CMD Cable TV. Same time every Wednesday. Keep safe and God bless. Signing off.